Thank you, David. Thank you, everybody, for being here. Thank you to everybody who's tuned in. So let me get started. I have a limited amount of time. The clock's running. The solar system is old. We have little time here. I'm a planetary dynamicist. That's a mouthful and a pretty esoteric profession. But as a planetary dynamicist, I'm especially tuned to two mathematical things about planets: the shapes of their orbits and their period ratios. So I like numbers. So about 2 years ago, when astronomers started noticing some peculiar patterns in the Kuiper belt, this belt of small planets beyond Neptune, we call them minor planets or Kuiper belt objects, I tuned into their orbit shapes and their period ratios. And I stumbled onto a new idea that may help us discover a new planet in the distant solar system. Searching for a distant planet in the solar system is a story about human imagination and curiosity and increasing intellectual and technological sophistication. It's also about being human, about our curiosity about the universe, about seeking knowledge of our place in the cosmos. So I'm going to start with a brief history of this very human enterprise. Ancient civilizations had a very simple concept of the cosmos. Okay, so we live on Earth. The sun and the moon rule the sky and our daily lives. And the afterlife is in heaven above or hell below. Very simple. Okay. With more data of the long-time cycles in the sky, humans developed a more sophisticated model of the universe, a more sophisticated conceptual model of the universe. There were the distant fixed stars, the 7 wandering stars, all gods and demons that ruled over our lives and over the cosmos. In time, with even more data and even more mathematics, a more precise model came to be accepted. That's the Ptolemaic model that you see up there. This was a combination of circular paths. Everything in the universe was perfect. Circles are perfect. Spheres are perfect. And this was a highly successful model. It was really accurate in predicting the cycles in the sky, and it was accepted for more than 1,000 years. Okay? Predicted the seasons, everything that we needed for human life, agriculture, and so on. Then, in the dawn of the 17th century, Galileo upset the elders with a new technology. He pointed a little telescope to the sky, and he discovered that not everything in the heavens turns around Earth. There are worlds turning around Jupiter. The sun was not perfect. It was blotchy. The moon bore mountains and valleys like Earth. And the evening star, Venus, ran phases like the moon. So ceding the center to the sun, the heliocentric cosmos grew in acceptance. A mechanical model of the cosmos emerged, beginning with Kepler's laws of planetary motion and leading to Newton's law of gravitation. The cosmos, it was finally realized, was ruled by natural laws. Shortly after that, with a bigger, better telescope, Sir William Herschel in England discovered a new planet in the solar system, Uranus, a planet that was unknown to the ancients. And this discovery truly opened human imagination to the possibility of more planets and more objects in the cosmos, more than we could see with the eyes before. Meticulous analysis of the slow movement of Uranus to seek the telltale fingerprints of gravity, of the gravity of planets now, of even more planets, led a French mathematician, Urbain Le Verrier, to predict the exact location of the unseen 8th planet on the night of the 23rd of September, 1846. Okay, on that night, one German astronomer turned his telescope to the sky and actually found that planet at the location that was predicted on that same night. And this was a triumph of 19th century mathematics applied to the cosmos. Now, the most famous search for Planet 9, so I'm here to talk about Planet 9. The most famous search for Planet 9 was that of Percival Lowell. This is his observatory. He was convinced that the movements of Uranus and Neptune were sufficiently aberrant that there was a large planet beyond Neptune. And he started a systematic search in 1906 at his observatory in Flagstaff, Arizona. That's my adopted home state. And this was the first observatory located remotely to do the best astronomical photography ever. Now, Lowell died in 1916, but his search continued. The sought-for planet was found in 1930 and was named Pluto. Okay? A shout out for Pluto. Plutophiles here. Well, more than 2 decades of searching for this planet is truly a story of persistence. Okay? A man's life and generations of astronomers have been persistently looking for objects in the sky. The size and mass of Pluto, however, took even longer to settle, not until 1978 when its moon, Charon, was discovered. And alas, then it became very clear that Pluto is smaller than our own moon, than Earth's moon, and hence only a distant cousin of this planet that Lowell was searching. Well, the hard work of following Pluto's movements over many decades revealed many surprises about this little planet, the shape of its orbit, and its ratio with Neptune's, okay, the things that I tune into, that my mind tunes into. Pluto's orbit is very elliptical. Okay? It overlaps Neptune's orbit, but these two never collide. These two planets are in a celestial partnership known as orbital resonance. So Pluto makes 2 revolutions around the sun in the same time that Neptune makes 3. And in such a way that the two are never in the same place when Pluto is at perihelion. Okay, so that makes them never collide. They kind of dance around each other. So calculations of the 3-dimensional geometry revealed, look at this beautiful picture of Pluto. This is the symmetric, grand path that Pluto makes if you're on a carousel rotating around the sun with Neptune's orbital period. Watch this, the symmetry of Pluto's orbit. This is this resonant orbit, and we'll run into resonances constantly again. So the 3-dimensional geometry of Pluto's orbit is also really fascinating. There is actually an additional resonance, more subtle. Pluto reaches perihelion when it's farthest away from Neptune's orbit plane. Okay? So Pluto's orbit is tilted, it reaches perihelion when it's far up, away from the plane of the solar system. And over time, it only wobbles slightly around this geometry. So altogether, Pluto is in what's called the periodic orbit of the 3rd kind, one of a class of orbits identified by the 19th century French mathematician Henri Poincaré. Such orbits have a resonant period and a specific tilt to the planet. The gravitational forces, so these are really fascinating orbits. The gravitational forces of the planets on each other have a special respect for these resonant patterns, and we'll run into this again with Planet 9. These peculiarities of Pluto's orbit kept celestial mechanicians really busy for many decades, and as a graduate student, I learned about these puzzles of Pluto, and I wondered, how did Pluto get to be so, this peculiar planet? And I proposed an answer. I proposed this answer that you're seeing in this animation here, giant planet migration, that the giant planets, Jupiter, Saturn, Uranus, and Neptune, formed in a very narrow annulus around the sun, and then later spread apart. I calculated that as Neptune slowly spiraled outward, an originally circular coplanar Pluto was shepherded into this resonance and transformed into this elliptical, tilted orbit. Now, lucky for me, for an astronomer, it's really lucky that subsequent discoveries over the few years after I proposed this idea, discoveries of the Kuiper Belt, many small planets beyond Neptune that are in resonance with Neptune, have bolstered this hypothesis of giant planets migrating. So our planets didn't form where we see them today. Computer simulations suggest that Uranus and Neptune and possibly additional giant planets were shaken up, scattered for a long time, for millions of years, before settling into the orbits we observe today. Now, more recently, hints of a massive planet in the very distant solar system have been noticed. The orbits of the most distant Kuiper Belt objects are kind of clustered. They're not randomly oriented. as we might expect. So if a distant planet, the true planet 9, not the little Pluto, if a distant planet 9 is shepherding these Kuiper Belt objects, we would like to know how massive is it, where is it orbiting? Now, computer simulations tell us that the planet is up to 10 times Earth's mass at somewhere between 300 to 900 times Earth's distance. Okay, but these simulations tell us nothing about its position in the sky, where it is in its orbit at the current time. Where would we go look for it? Now, when I looked carefully at the data, I noticed another intriguing pattern. Okay, numbers again. You didn't expect to see tables here, did you? So what I noticed was that the ratios of the orbital periods of the most distant objects are close to small whole numbers. Now, this could be mere numerology, or it could be a real clue. It could be a real clue if a massive planet, and it could be a real and valuable clue, I'll show you, were indeed shepherding these Kuiper Belt objects in orbital resonances. If a planet were indeed shepherding these Kuiper Belt objects in resonances, then we have some clue as to where the planet is, just like Pluto's resonance with Neptune. If we know Pluto where Pluto is, we know where Neptune is not. It's not near Pluto's perihelion. So I searched for an orbit of planet 9 that would be resonant with the distant Kuiper Belt, these Kuiper Belt objects. There are only a small number of possibilities, of likely possibilities. The choice most consistent with the orbital clustering that we've seen is an orbit period near 17,000 years. A very long period. So this planet is moving really slowly in the sky. This singular choice of planet 9's orbit period leads to simple resonant geometries of the distant Kuiper Belt objects relative to planet 9, like the shapes that you see on the screen now. These shapes of the resonant orbit show us the portions of the orbital path where this hypothetical planet cannot be at the current time. In addition, there are only two choices or two approximate choices of the tilt of this planet's orbit. One is that it's either close to the planes of these distant Kuiper Belt objects, or it follows the Poincaré's periodic orbits of the third kind that I mentioned before, so it has a specific tilt. And those two choices turn out to be one that's about just 18 degrees tilted to the plane of Earth's orbit. The other one is tilted 48 degrees to our planet's orbit. It remains now to refine our mathematical predictions and test them with telescopes to prove that this planet really exists, or if perhaps the apparent patterns in the distant Kuiper Belt are a fluke, a statistical fluke of a small sample. We only have about a dozen objects giving us these clues. So should we find planet 9, it will be a triumph of both mathematics and advanced astronomical technology. Again, yet again. What will it mean to discover a distant large planet? Well, we will have a more complete inventory and a new self-image of the solar system. It may make horoscopes more accurate, finally. Well, for scientists, it will stimulate new research on the origin of comets. This planet 9 roams in this reservoir of frozen-in bodies, the remnants of our solar system far out in the distant solar system. How does it affect the frequency of comets that come to us so we can see them in the sky? It's going to change our ideas about how comets arrive in the inner solar system. It will also stimulate new research on the formation of the solar system. How did the solar system manage to look like this clockwork mechanism that Newton and Kepler believed in, despite having this history of scattering of planets? Almost surely this planet was scattered from closer in. Are there even more planets roaming in the distance? How did the scattering of this planet affect the course of our own planet? It almost surely did. So planet 9 will provide a new challenge and a new destination for future exploration. And I thank you.